we're now officially onto a new chapter of the notes. So this is all the stuff that's going to be on the second assignment. So last chapter we were really, if you look at everything we did involved the subset relation in some way. Like anti-chains are very, involving the subset relation. Downsets, right? A downset is like defined in terms of subsets. The kind of focus of this chapter is extremal theorems or extremal results on intersections between sets. So, A intersect B for some sets A and B. So today we'll look at kind of the most natural of these. Extremal, yeah. Basically, extremal, like when I say the word extremal, I really mean maximizing or minimizing something. So like Sperner was like extreme in this, extremal in the sense that, Sperner was saying, what's the biggest size of an anti-chain? So how, so these are all going to be about maximizing or minimizing some parameter with respect to some conditions. Yeah, that's a good question. I mean, yeah, when you write an optimization problem like a linear program, right? It's like you have an objective function, you're maximizing subject to constraints. There's really no difference in some sense. Although, I guess in say an LP or something, you've got different, you have a type of constraint and the constraints can change. Whereas here, we're sort of fixing a single type of constraint, like it's an anti-chain, for example, and we're maximizing subject to that. But really, in some sense, there's not that big of a difference. It sounds cooler. Yeah, it's extreme. It's like, I don't know, motorcycle combinatorics or something. Okay. So here's the key definition for today. An intersecting family. So say that a collection F of sets is an intersecting family, or probably most of the time I'll just write, so saying F is an intersecting family is the same as saying F is intersecting. That's probably a more kind of efficient way of saying it, and that's what I'll probably say most of the time. So say that F is intersecting, or it is an intersecting family if all the sets intersect. So A intersect B is non-empty for all A, B in F. Okay, and the main focus today is an extremal question about intersecting families. So what's the maximum cardinality, so the maximum size, the size of script or curly F. So of an intersecting family F contained in, let's say, the numbers 1 up to n, choose K. Or, in other words, the sets of size K. So we want to maximize the size of F subject to the constraint that it's intersecting. Okay. So okay. I mean, the general definition, by the way, just so we don't get any confusion, like, if I say something is intersecting, I'm not necessarily saying the sets have the same size, right? F is just any family of sets. This will come up on the assignment, like in terms of thinking of different sizes of sets. But yeah, the question we're going to focus on today is, what if all the sets have size K? How big of an intersecting family can you have? That's a good observation. I think that's coming pretty soon. Yeah. But if maybe, we can kind of say it now that, if K is bigger than n over 2, it's going to be pretty hard to have two sets that don't intersect, right? Everything intersects if K is bigger than n over 2. So the answer is going to change depending on what the value of K is. Let's do a poll. So let's say, just to get used to the definition, and because I think probably people are familiar with thinking about sets of size 2, because that's kind of like graphs, right? A set of size 2 is like an edge of a complete graph. So how big, so suppose n is at least 4, how big can an intersecting family be in the sets of size 2? Now, like, you're not supposed to know the answer to this already, so but just a guess, essentially. I'm not even sure how I would necessarily kind of reason this, right? I've got 4 points. Once you've drawn 2 sets, so I'm going to draw the sets as edges in a graph, right? But okay, 2 sets have to intersect, so that has to look like this. If I have a third set, okay, and let's say I've got 4 points in total, it's got to hit both of these edges, so it's either got to look like, a cross, or it's got to be, like that or something. I think if you think about it long enough, it becomes fairly clear that the best answer is to take a star, take a whole bunch of edges or sets of size 2 that all contain the same point, right? And that's going to have n minus 1 sets. Okay, so yeah, I think fair enough to not know that one because we haven't answered that question. But just to get you thinking about it, if you have sets of size 2, then just taking all the sets containing a given point, that's going to be the best thing. Okay. Now this addresses comment. If k is bigger than n over 2, like for example, n is 5 and k is 3, for example, suppose I have 5 points and I take sets of size 3, well, they can never be disjoint. They always have to have something in common because they're too big. So, as I was suggesting, the answer to this is n choose k. Because actually, you can just take everything, intersect. Is that clear? So this is sort of a case which is not particularly interesting. But now what if we let k be at most n over 2? So that's where we really get into the meat of this problem. So any guesses? So I won't put this one to a poll, but how big can you make an intersecting family? Yeah, so there's an answer in the chat. How do you figure that? N minus 1. Oh, it might be on the back of my slide. I'll obscure it, or on my video. But there's also so I'll assume that so probably pretty much the only way you could come up with n minus 1 choose k minus 1 is kind of emulating the case k equals 2, right? In k equals 2, we just fixed the point and we took all the edges or all the sets of size 2 that contain that point, right? That's going to work here. So we've got another answer coming in, which is 2 to the n minus 1. You might be thinking of if f is a subset of this, right? But I'm picking it from the sets of size k. But if you're thinking in terms of this, then that's going to be on your assignment. So I won't really address this case. But yeah, so if we let f be all of the sets a contained in 1 up to n, such that the size of a is k, and that the number 1 is in a, that's going to have size n minus 1 choose k minus 1. And it's going to be intersecting because if you take two sets in there, their intersection contains the number 1, so they're intersecting. So that's the lower bound. And in fact, that's turns out to be the answer in this case. Well, that's what I'm going to spend the rest of the time proving, that that's the best. But actually, and you can, in most cases, you can even prove that that's the only best option, like that's the only optimal solution. But actually, in the case where there is a sort of interesting boundary case where k is equal to n over 2, like if n is even, in which case actually there are many optimal solutions. But anyway, yeah, so the reason that this is optimal is what we're going to focus on from here forward, basically. So are there any questions about this? So maybe I think the next thing, yeah, right, where, yeah, partition, I guess, is, you have sets which are all disjoint and they all union to everything or something. I guess, yeah, that's that's sort of like the opposite in some sense, isn't it? Yeah, pairs of disjoint sets. But then it becomes kind of easy to say how big can it be or something, right? You just put everybody into its own little bin. But yeah, that's a natural kind of opposite to that. I mean, yeah, if we were kind of trying to follow the path we did to prove Sperner's theorem, maybe looking at the opposite, like looking at we looked at chains and anti-chains, and that helped us. But yeah, in this case, yeah, your microphone is amazing, by the way. Anyway, okay, yeah, like I was saying, the case k equals n over 2 is interesting. Yeah, maybe I'll just say a little bit about this. So if k is n over 2, if we take the sets, like if the size of a is k, then you have these complementary pairs, a and n minus a, and they both have size k, right? Because n is 2k. In this case, you get something weird, because if I list out the complementary pairs, And if I just take one from each of them, so I just say, on this one I'm taking that guy, maybe for another pair of sets B and n minus B, like in some sense, which one I called A and which one I called n minus A is arbitrary, but anyway, I can take that one. And if you think about it, that's always going to be an intersecting family as well, because if I take a set of size k, the only set of size k it doesn't intersect is its complement, if n is equal to 2k. Turns out this actually gives the same number, so it'll give you a half of n choose k, which is n choose n over 2, or maybe I should say, I don't know, 2k choose k, let's say. K n is 2k. In this case, that actually equals, if you look at Pascal's identity, this actually equals that, which is again n minus 1 choose k minus 1. Okay, so this is just like another tight construction in a very special case. And it gives you lots of tight constructions. No matter how I choose one of each complementary pair, it's going to work. Okay, any questions about that? Okay, so far this is just a bunch of examples. So let's prove a theorem, maybe. Let's see. What do I want to do here? Oh, no, this is, I think, just the same example I gave earlier. Right, so the Erdős Theorem it gives the answer to this question. So if f is a subset of the numbers 1 up to n, or choose k, so it's a collection of subsets of 1 up to n of size k, and if it's intersecting, then, so this is, of course, an important hypothesis that k is at most n over 2, then it has at most n minus 1 choose k minus 1 elements. So therefore, these two constructions we've seen are tight. Okay, so is the statement clear before we move on to the proof? So I've got it restated at the top. So just a kind of sort of definition. So I'm going to write the integers, subscript n is just z mod nz. Like it's the integers modulo n, basically. So it's the numbers 0 up to n minus 1. Where addition, when you add two things and they go over n, then you subtract n until, anyway. It's the remainder mod n, basically. So think about the integers modulo n as being on a circle. Okay, so 0 is somewhere, and then we've got 1, so whatever, I guess I'm going clockwise here. Imagine they're on a circle, right? So I'm going to say an interval is basically a kind of set of consecutive numbers on the circle. So formally, an interval is a set of the form I plus 1, I plus 2, blah, 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 up to I plus t, where I and t are some numbers between 0 and n minus 1. Okay, and the addition is modulo n. So here I would have I equals 5. So I tells you where the starting point of the interval is, and t tells you how long the interval goes. So it would be t equals 1, 2, 3, I guess. And here we're dealing with n equals 7 in this case. So far, nothing to do with intersecting families, but we're just setting up the definitions that we're going to need. Okay, so here's a question for the audience. How many bijections are there from 1 up to n to the integers mod n? First of all, hopefully there is a bijection, so they have the same size. But how many bijections are there? Yeah, it's interesting when you write n factorial with a question mark, because it looks like I think the name for that thing is like an interrobang or something, like like you're shocked or puzzled or something, right? But the answer is n factorial, right? Just this is a kind of math 222 thing or something, right? N choices for the first, n minus 1, n minus 2, all the way down to 1. Okay, a little bit more of a trickier question. Suppose I take A, so I take a subset of 1 up to n. How many bijections are there such that f of A is an interval? Remember, an interval is like some consecutive numbers in Z mod n. What did I say here? A hint. Oh yeah. So I guess I'm saying, let's say that the size of A is k, just to make our lives easier. So how many, so I guess, so the hint says, how many bijections map A to 0 up to k minus 1, and then you can think of, okay, how many intervals are there, and then multiply by that. But so let's think of that kind of sub-problem. How many bijections have the property that f of A is 0 up to k minus 1? This is kind of similar to something we did in the lim inequality, because we were looking at permutations that start with the elements of a set A or something. It's kind of the same. But any thoughts? Is the question clear? I know I always end up scribbling all over things, but that kind of thing is going to work in some sense, like, except it's sort of like you only have two different types of letter or something, I think, in this, in the sense of, or it's similar to that. Okay, so this is like, so we've got an answer which actually goes to the final answer here. So the kind of, okay, so for the sort of sub-problem type thing, right? If I want to map A bijectively to 1 up to k, or 0 up to k minus 1, well, first of all, how many, so like, basically if you look at A, you say, go through the elements one by one. How many choices do I have for the first element of A? You have k, any of these, then you have k minus 1, k minus 2, all the way down. So if you think about it, you've got k factorial ways to map the elements of A, and then you have n minus k factorial ways to map, because they have to map everywhere that's not this. Okay, so that's solving the number of ways to map f of A to this. If we want to map it to a general interval, well, we know how many ways to map to this interval, so you just now go to the next interval. It's the same, in terms of if you want to map to 1 up to k, for example, and so on and so forth. And if you think about it, there's n intervals that have length k, and we obviously have to map it to an interval of length k. So that's how one gets the answer that's in the chat. Okay. So we're gonna come back to this. We're gonna use this stuff. But so what we have to do is let's understand this idea of mapping to intervals and the intersecting property, and how they kind of interact with each other. So here's my claim. Suppose that f is a bijection from 1 up to n to the integers mod n. So it's a bijection. I claim that it can only, the number of sets in F that map to an interval is at most k. Remember, F is a subset of, so the k comes from the hypothesis. F is a subset of this thing. Okay, so why? So the way to kind of argue this is, suppose you've got something that maps to an interval. Well, maybe I'll just draw a circle. So my circle is Z mod n. So start with something. If nothing maps to an interval, then we're done, because certainly 0 is at most k. So there's at least one thing mapping to an interval. And that interval is the interval from I, which way am I going? Clockwise, I guess. I up to I plus t, or k minus 1, because, it's an interval of length k. Well, by the fact that it's intersecting family, we know that, anything in F has non-empty intersection with A. So everything in F intersects this interval somehow. And what if it, what does the picture look like if F of B, so A intersect B is non-empty, and F is a bijection. So actually, F of A intersect F of B. Maybe the bijection thing doesn't even matter. No, it doesn't, I don't think. F of A intersect F of B is also non-empty, right? Because you just take the common point of A and B and look where it maps, and that'll be an F of A and an F of B. So what I was going to ask, what if F of B is an interval? Yeah, I should have started with that probably. A is something in F. Yeah, good question. Yeah. So I'm just starting with something which is in F, and then I'm going to kind of something which is in F and maps to an interval, and then I'm going to try to say some stuff about it. if nothing mapped to an interval, then the answer is, I've got 0 things mapping to an interval, and that's good enough, Okay, well, if f of b is an interval, basically it's got to look, it doesn't, I don't know which way it goes, but it's basically an interval that kind of, it's an interval that intersects that interval. So it kind of slops over in one direction or the other by some amount, right? And it's an interval of length k. Now, think about it. If I've got a bunch of intervals of length k, they're all different intervals. How many of them can intersect each other? So maybe I've got a third set which maps to an interval. If that third set maps to an interval, it has to also kind of intersect these two somehow. So this is now getting kind of dodgy because it's barely intersecting the blue one, or indigo one, or whatever that color is. And yeah, so it's kind of barely intersecting there. So basically, if maybe that works to argue it. If I kind of take the middle point of the union of all the intervals, you can only be k over 2 this way or that way, kind of thing. Maybe what the way I'll argue it is kind of take the also I should maybe point out something, that it's important that k is at most n over 2 here, because this picture only works if k is at most n over 2. If k is bigger than n over 2, you could have intervals that overlap because they wrap around a little bit, right? So I think this is the only place we're going to use this assumption that k is at most n over 2, because you've got, if it was bigger than n over 2, you could have that. But since it's not, basically if I take the smallest, or it's a bit difficult to say biggest and smallest here, but I kind of take the point which is furthest on this side, the furthest starting point in that direction. Basically the last starting point, the latest it could be is the last element of that interval, right? And so I've got this point here is a starting point. This is a potential starting point. That's a potential starting point of an interval all the way up to the last element. And there's only k possible starting points. Okay, so this is maybe not the most formal proof, but is this more or less clear? Basically, if I just look at the furthest over interval, every interval which is the image of a set in our collection must start at one of the points of that interval. And there's only k of them, so only k of them can be intervals. Only k of them can map to intervals. If that was true, if there was already an element that's in every set, we'd actually be done. So actually, we're not gonna assume anything like that. But if there was, you actually will get one point that's in all of them, because like this large, if I take the kind of furthest interval on, maybe my video is mirrored, I don't know, but the furthest interval this way, and then I take, like, that point will end up being in all of the sets that map to intervals. That doesn't mean it's in all the sets in F though, because there could be another set in F containing, say, like containing this point, because all I'm analyzing here is the sets that are intervals. So it could contain these points, that point, and that point, right? That could be a set in F, and it might not contain the point in the middle. But you see this orange thing, if you can see it anymore, it intersects all the other sets. Yeah, the counterclockwise-ist set is what I want to start with, and then I want to go along. Yeah, that can be written properly, but I think the picture is kind of the best way to explain it. Okay, so at most k, so whatever bijection I take, I can't have more than k sets that get mapped to an interval. That's what we've proved. So this final bit of the proof is actually pretty similar to what we did in lim. It's a bit of kind of double counting. So on one hand, I'm summing up so let's look at this first sum here. I'm summing over all the bijections f from 1 up to n up to z mod n. I'm counting how many elements of the collection get mapped to an interval. So for how many, so maybe I could have written this as cardinality of a set, but I've written just this number thing. So the number of elements of f such that f of a is an interval. And what we said is that each of these summands is at most k. So I mean, the number inside the sum is at most k. That's what we just proved. So the total is at most n factorial times k, because n factorial is number of permutation, or number of bijections. But this same sum can be counted like from the other perspective, in a sense, kind of changing the summation in some sense. Like if I sum over all f and I count the number of a such that f of a is an interval, that's the same thing as summing over the a's in f, and then counting the number of bijections for which f of a is an interval. So this is like a genuine equality. Is this clear? It's kind of like changing the order of summation in some sense. Although I haven't written a double sum, but it is kind of changing the order of summation in some sense. Basically, both of these things count pairs fa, where f is a bijection and a is a set, such that f of a is an interval. You could count that by summing over the f's and counting how many a's they correspond to, or summing over the a's and counting how many f's they that they link up with or correspond to. Okay, and we actually calculated this this other way of writing the sum. We gave an exact answer. So this thing inside of the sum is just k factorial n minus k factorial times n. So that's what we proved earlier. So this is just the size of f times n times k factorial n minus k factorial. Okay, maybe, yeah, so, yeah, do you mean the equality of these sums, or the idea of, so there's a question about like the confusion about the idea of bijections that map to interval. Yeah, so just, z mod n, you've got, so an interval is just a set of consecutive points on this thing. And let's say if k is 4, then this is an interval of length 4, of length k or whatever. And yeah, so if I take 1 up to n, right, and I take a set A of size 4 from there, I mean, there's going to be a certain number of bijections. Like 1 up to n and z mod n have the same size, so there's a bijection between them. Some of those bijections will map A to an interval. For example, if I just take, so suppose A is like 2, 3, 4, 5, or maybe 2, 3, 4, 6, right? And maybe I map 2 here, 3 here, 4 here, 6 here. And then I map the rest of, so I guess n is 8. I map the rest of the numbers there, and that's just that's a bijection which would do that, which would map A to an interval. Okay, but maybe I should kind of, well, actually, to be honest, to finish this proof, it's just a bit of algebra now, right? We just divide. This is a super slick proof, yeah. It is at this point just algebra. So I just divide. I mean, I want to bound on the size of f. So I just divide everything by this junk, and I get that f is at most n factorial, but I've got an n here, so that cancels a little bit of that. So I've got n minus 1 factorial left over, yeah, a little bit of this k factorial cancels with that, so it's k minus 1 factorial, and then n minus k factorial. So it is just the binomial coefficient there.